Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on September 13th, 2025, about 3 days ago. This paper shows a unified embodied foundation model that pairs coherent step-by-step reasoning with low-latency control, delivering over 8% average improvement in reasoning and navigation performance. The paper is titled Nav-R1, Reasoning and Navigation in Embodied Scenes. And as we will see later, the results are really impressive. It combines a large chain of thought dataset, multi-objective reinforcement learning, and a fast and slow control design with real robot tests confirming robustness. Also, the author shared a GitHub repo. You'll find the official README with a project overview, a teaser video, citation info, and a clear intro to Nav-R1's dataset, GRPO training, and fast and slow reasoning. The assets folder is included, plus a TODO noting upcoming code, dataset release, and a Hugging Face demo. Alright, Figure 1 illustrates how the system unifies dialogue, reasoning, planning, and navigation so a robot can understand goals and move through a home. The scene map shows start and target markers, which indicate where the agent begins and what object it must reach. The green, yellow, and purple paths depict step-by-step choices that connect high-level instructions to concrete moves. The bottom panels summarize example conversations, plans, and navigation steps. So, Table 1 summarizes the data sources that feed the Nav County T110K dataset, which matters because broader scene and task coverage leads to stronger generalization. The table contrasts public benchmarks across scenes, task types, instruction modality, and environment settings. The key point is scale and diversity. The new dataset spans 342 scenes and 110K tasks with vision, language, and point cues in continuous environments. That breadth supports both object navigation and vision-language navigation. So, Figure 2 explains how fast and slow reasoning lets the robot think deeply while still reacting quickly. The slow system aggregates semantics across images, depth, point clouds, and language, which means it forms a longer memory of goals and layout. The fast system reuses later transformer blocks to output low-latency actions, so control stays responsive. Asynchronous sampling gates how often each system updates, and low RA adapters tune only late layers. While Figure 4 lays out how the reinforcement learning pipeline turns text and images into actions while scoring 3 complementary rewards. The left block shows group relative policy optimization, which compares the policy to a reference using a KL penalty so updates stay stable. The center block defines understanding reward, combining exact answers with a CLIP-based semantic score, meaning images and text align in meaning. The right block defines navigation reward from path distance and endpoint accuracy, and the bottom ribbon enforces strict output format for structured chains of thought. Table 2 shows that the method leads object goal navigation on HM3 DOVON, which means the agent finds target objects more often and with straighter paths. Success rate is the fraction of episodes that reach the goal, and SPL balances success with path efficiency. Against behavior cloning, Dagger, and recent zero-shot systems, the approach posts the highest scores across scene, scene with synonyms, and unseen splits. The gains suggest coherent reasoning plus fast control translated into reliably shorter, successful trajectories. So, Table 3 shows that the approach leads instruction following navigation on the R2 RCE and RX RCE unseen splits, even without simulator, pre-trained waypoint predictors. The table lists which sensors each method uses, then compares navigation error, success rate, and SPL, which balances success with path efficiency. The bottom row reports the strongest scores across both benchmarks, so the gains hold despite other methods adding depth, panoramic views, or odometry. This means coherent reasoning plus fast control translates into higher success, with shorter, more accurate paths. Wrapping up, 2 takeaways stand out. Structured chains of thought plus group relative policy optimization rewards produce coherent plans that actually move robots to targets, and fast and slow reasoning delivers those plans with low latency. The broader implication is practical embodied agents that think and act reliably in real homes. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.